So this is joint work with Moritz, Kerz and Florian, Strunk. And let me maybe make the convention here. So first of all, I want to say that, so this is about K-theory, and K-theory for me is always non-connective algebraic K-theory. So there's some of the capacity loop of K-theory. And so the rings that appear in this talk are all just ordinary discrete rings, commutative and so on. So in particular commutative. So this is not necessary for all the statements, but somehow every time you can prove something, it's for discrete commutative rings. Okay, so now let me make a definition. So the ring A is called Kn regular. Somehow if its nth K group is homotopic invariant in the polynomial direction, so if and only if the map from Kn of A to Kn of any polynomial ring over T1 to Tr, if this is an isomorphism for all R. Okay. So in general, this is not true that you have this isomorphism, that these new terms appear that we heard about yesterday in Wolfgang's talk. But there are a number of examples somehow that satisfy this property, so let me give you some examples. So let's say, so I give you a list of examples of rings which are somehow accidentally Kn regular for all n. So n is some fixed integer. So maybe Kn regular for all n. So the first thing is some of the classical example, namely that if A is Noetherian and regular, then it's also Kn regular. And I mean, this is where this name comes from. So this was first proven by Hausdorff and Q. And maybe let me recall what regular means. So in general, there are several possible notions of regularity. And in the Noetherian commutative case, they all agree. And also they have a very nice geometric description in this situation. Here, so let me just recall. Regular means that for all maximal ideals, you can look at some of the cotangent space of the local ring at the maximal ideal, so m mod n squared. This is a vector space over the residual field, so over a mod m. And the condition that the ring is regular is that this dimension is the same as the Kull dimension that we have. So we expect that the cotangent space is not too large. So this is the dimension of the Kull dimension of the local ring here. This is the definition of regularity. And I recall this here because this is somehow what we will explicitly check later on in the proof of some theorem that I haven't announced so far. Okay, so this is the first classical example, and the next one, which is more recent but could have been proven also maybe at the same time, is all valuation rings are Kn regular for all n. And this was first observed, I think, maybe in parallel in our work, and also by Shane Kelly and Matthew Morrow independently. The proof is a bit different, in fact, but so some of these two examples fall in a bigger class. Maybe they are what is called stably coherent and weakly regular, or sometimes called weakly regular, which means just that every finitely presented module has a finite resolution by finitely generated projective ones. Yeah, so this is what you need to compare some of K-theory of projective modules with G-theory, so K-theory of coherent modules. And for the G-theories, basically you can use self-proof or print proof that this is linear. Okay. Then some of the third examples of different. So all commutative C-star algebras are Kn regular for all n, and even you can take a commutative C-star algebra and tensor over a C with a smooth C algebra, and this is due to Cortiñas-Haesemeyer-Weibel. With some preliminary summary by Rosenberg. And
already three, are you just considering them as discrete rings?
Yeah.
Sorry, for your system algebra is over C or over R?
Over C.
Over C.
And the last example is which is quite recent. Also, you can look at something like this. So smooth algebra. If you have a smooth algebra over a perfect Fp-algebra. So if you have an Fp-algebra, then you have the Frobenius map, Frobenius homomorphism, and you call it perfect if the Frobenius is an isomorphism. And then, in particular, all the perfect Fp-algebras are Kn regular for all n, and even you can take something smooth over perfect. And this is due to Antio. Matthew and Matthew model. So this appeared maybe just, I don't know, this or last year. And yeah, so just as one fact maybe which is not relevant for this talk, but these two classes also have no negative K theory. This is also something which you classically have for regular rings. And in these two examples, you usually also have negative K groups. Okay. Any questions so far? No. Okay. So this Vorst conjecture is somehow converse to this first statement. So you want something. You look at Noetherian rings, and you ask when they are. You assume they are Kn regular. Are they indeed regular? So is this an equivalent statement? And so one thing you can easily see is if A is K1 regular. Because we are commutative, the units are always a direct sum in K1. So you see, in particular, the units are homotopy invariant, and this directly implies that there can be no nilpotent elements. So this implies that A is reduced. This is very simple. So this is already some kind of regularity, or maybe very, very weak. But you see that if you now assume that if A is say Noetherian and zero-dimensional, so full dimension 0, which just means it's a finite product of Artin rings, then we see that if A is also K1 regular, then it implies already that it's also reduced, so then it's just a finite product of fields, so then it's regular. Okay, so there's some indication that the converse statement to this point 1 could be true. And Vorst proved somehow the one-dimensional case at least over fields, and then he made a conjecture, so that's the conjecture Vorst. There's some technical assumption, so he assumes that A is, let's say A is this side of it, is essentially a finite type. So this just means it's a finite type over a field. So finite type just means a quotient of a finitely generated polynomial algebra, and essentially means that you could take a localization of such. Okay? And then the conjecture is if A is K dimension of A, so the full dimension plus 1 regular, then this should imply that A is regular. Okay, so you see this
is localization and possibly infinitely many elements. So what can that mean? Is just localize finitely many? So you can just add on another variable and quotient by a relation.
Yes, but then you yeah.
So the point is
no.
You want
I mean
infinitely many elements.
no. I mean if it could happen that the dimension changes. I think.
Right, but essentially a finite type. It's essentially a finite.
No, I mean you could take it like some portion of a polynomial ring and then localize it the prime ideal.
Yes.
Yeah. So you localize many elements.
Is
there a relation between the various K n notions?
Yeah, this will come up later. So indeed it's true that if it's kn regular, then it's kn minus 1 regular. But I wanted to mention this later on because this is somehow needed, but anyway. Let me just say a little bit about the history, what is known here. So first of all, as I said already, dimension 0 case we just did, the dimension 1 case. This is what Vorst did, and I think 79. And then it's completely proven for Q-algebras. So it's so if this for Q-algebras. This was proven by Cortiñas-Haesemeyer and Weibel in 2008, I think. And then there was also a conditional result in positive characteristic by Lars Hesselholt and Thomas Geiser. So let's say, and actually a more restricted version. So if A is for A really a finite type over a perfect field of positive characteristic. This was, and also assuming a resolution of singularities. This was proven by Geiser and Hesselholt. In 2012. Okay. So now I also want to prove a result in positive characteristic, which in particular gives you this Geiser-Hesselholt result, but it does not precisely prove this conjecture in the positive characteristic case, because somehow what we don't get here is this dimension bound. So there's some junk somehow coming from. So if you have a base field, then it comes from the base field. So it's like this. And to formulate it, so I first have to introduce a notion. So let's say first if F is a field of positive characteristic of characteristic P, then we define a notion called the P dimension. Somehow, so you will see where this comes from, why this appears. This is, by definition, it's the dimension over F of the Kähler differential forms of the absolute Kähler differential forms of this field F over the integers, if you like, or it's actually the same if you could also take the over Fp here. Or in fact, you could also take the dimension, it's all the same module, over the subfield of F generated by the pth powers. So, and this will come up essentially from the methods that we use, which use trace methods, and at the end reduce something to differential forms. So this is where this comes from. And let me just maybe mention as an example. So, F is perfect if and only if the p dimension is 0. This is so in some sense, the p dimension is a measure for how imperfect your field is. So one direction is very easy. So if it's perfect, then any element x is of the form y to the p. That's the standard thing in somewhat differential calculus in positive characteristic. So you see, I mean, this module here is generated by the symbols dx. And you have the Leibniz rule, so you get dx is p times y to p minus 1 dy, and because we are in characteristic p, this is 0. So you see that the module is 0. The converse direction is also not hard, but it's a bit longer. Okay. So that's the p dimension of fields, and now we can also define more generally the p dimension of commutative rings or of schemes. So if x is now an fp scheme, and then we define the p dimension of x as so the supremum, following supremum. We look at somehow all points of the scheme. How do you write this? So and then for every point we look at the usual dimension of the local ring, Ox, x. And if you just and this is for x. runs in text. If you just write it like this, then this is just the usual dimension of the scheme. And we correct this somehow by the p dimension. Sorry, we'll write this again. By the p dimension of the residue field at this point. Yeah, so that's the definition, and it turns out this has good properties. So let me just say that, for example, if your scheme is of finite type over a base field, so if X is a finite type over a field F, then what you get is that the p dimension of your scheme is just the usual dimension, the full dimension of the scheme, plus the p dimension of the base. So it's somehow you have some control on this. And also, so there's a similar statement if you have a complete local ring, then the p dimension is just the usual dimension of the ring plus the p dimension of the residue field. Okay, so this is something that we use at some point. And with this I can now formulate the main theorem. So it's theorem A. So if, let's say A is, there's one technical condition that we need in the proof. We need A to be excellent. And if you then Fp-algebra. And then one more finiteness condition is that we also assume that for all points in the spectrum of A, we want that the residue field, okay, you can say like this, that the residue field is finitely generated over its pth powers, the subfield of pth powers. And that's equivalent to asking that the p dimension of all the residue fields is finite. These are some technical conditions. Let's say you have this, and then the conclusion is, so if A is k p dimension plus 1, k regular, and then k is regular. Okay. That's the statement. So you see this.
Sorry, I mean your condition just makes sure that this number is finite, right? Why didn't you just say the p dimension?
No, it could be. I mean, there's no uniform bound, so it could. I mean, we allow very general. I mean, this is a very general class of rings that we allow in physics, and the bound doesn't have to be uniform.
But then I don't understand what it means. K p dimension A plus 1.
You should have a constant there.
If it's infinite.
I mean, this could happen, that the p dimension of the whole thing is infinity, so then you just ask that it's kn regular for all n.
Oh, that always means,
and then it
like when you say k blah regular, it always means for all n less than that.
That's a good point.
Oh, now you're using this
Yeah.
accent. You didn't know.
Yeah, okay. Okay, let's
make a remark.
Yeah. Okay. So yeah, I will come back to this part. Yes. Let me just mention something. I don't know if this is really necessary. I mean, but anyway, this is, maybe you don't know what this means to be excellent, but it's basically it's used to compare a ring with its completion. So if you're in particular, it tells you that if you have a Noetherian local ring, the map, which is excellent, the map to its completion is what is called regular. So this is where it is used.
Can you make it to just it being a G ring then?
Yeah, probably yes. I think this works. I think. Okay. So I have how much time do I have?
If you make the comment that you don't know whether this is necessary, do you know that this dimension is necessary as opposed to what?
No, this I don't know.
You also know.
I mean, we need it definitely for the proof. I mean, otherwise, but this is maybe not necessary, and in fact, what was proved here. This also works in positive characteristics. So for curves, he doesn't need the p dimension, but he has completely different techniques somehow, and our techniques really need this, but it could be, I mean, could be true with the dimension. Yeah. So. Okay, because we discussed this, so there's a theorem B, which is a mixed characteristic version, which only works in the one-dimensional case, and maybe I skip this for now, but if I have time, I can come back to this. So now let's discuss this point here with the Kn regularity. So some facts about this Kn regularity. There's another point, maybe. It's of course an obvious question whether you could replace this ring here, also in the conjecture, by a general scheme. And this is definitely false. Okay, so it's really important to have affine schemes here. And the point is the following. So there's the following observation by Vorst. So if A is Kn regular, then it implies that any localization, like this S inverse of A, is also Kn regular. And this is something that does not work for schemes. So if you have a scheme which is Kn regular, then you cannot you cannot deduce that the local rings somehow are also Kn regular. That's the main point. But this is of course useful because irregularity, I mean, as we see from the definition in the geometric situation here, this is a local notion. So that's clearly helpful if this Kn regularity also localizes somehow. Okay. So in particular, you can reduce this question to local rings. And then you can, so this is not so hard to prove, but you just attribute it to Vorst. This now you can use for the following. So if A is Kn regular, I mean the same condition as here, then it follows that it's also A is Kn minus 1 regular. So this now finally we solved all these questions. And because, I mean, it's clear by definition, if A is Kn regular, then also the polynomial ring over it is Kn regular. So, but then by this fact here, you can localize at the variable. So you see the Laurent polynomials are also Kn regular. And then you use that also by this Bas fundamental theorem that we've seen yesterday in Wolfgang's talk, that the Kn minus 1 of the ring is a direct sum in Kn of the Laurent polynomials. And then you get the Kn minus 1 regularity for A. Okay, so this is good, and this in particular implies the following: that if A is Kn regular again, and then there's something called homotopy K theory, which somehow you start with algebraic K theory and force it to be homotopy invariant, and then by some spectral sequence argument, this implies that the map from algebraic K theory to homotopy K theory is n-connective, so more precisely the map from, let's say, Ki of A to homotopy K theory. I will briefly recall what this is. This is an iso for I less than or equal to n, and it's surjective for I is n plus 1. Okay, and here this KH is Weibel homotopy K theory is by definition KH of a ring. So the spectrum KH is by definition the geometric realization of the simplistic spectrum. Where you take the non-connective algebraic K theory, to the standard simplistic thing that appears in motivic homotopy theory, where this A delta P is just some of the algebraic P simplex. Okay. So this is simplistic spectrum, and then this condition here, because all these A delta P's are in fact isomorphic to polynomial rings, this fact here implies that you have this connectivity estimation. Okay. So now I want to sketch somehow how you prove these kind of results. And And this somehow is precisely based on this last observation that if you assume that your ring is Kn regular, then you have a certain estimate of the connectivity of this comparison map between algebraic K theory and homotopy K theory, and then you lead this to a contradiction. Or let's say, I mean, if you assume your ring is not regular, then you lead it to a contradiction. Okay, so how do you prove this? So this theorem A somehow follows from combining two things. So first of all, we prove a vanishing theorem for the homotopy K theory, or some variant of it. Actually, what we do is that we take the homotopy K theory with mod p coefficients. And this vanishing here means this vanishes, let's say, this mod p homotopy K theory vanishes roughly above the p dimension, plus, oh no, it's precisely like this. Okay.
Above the p dimension or minus the p dimension?
The p dimension, it vanishes, yeah.
Vanishes in positive, so the
in positive degrees.
Kh naught is 0, for example?
K above.
Oh, above, sorry.
Yeah. So it's, okay. If the p dimension is 2, then it vanishes in degree 3.
Can you do another?
And you combine this with a non-vanishing, and this is actually just a lemma for the K theory mod p. It's like this. And this not, so what you prove is roughly that, so first of all, I mean by this argument that I indicated, you can of course assume that your ring is local, and by this excellent thing and so on, you can even assume that it's complete. And then for complete local ring, you prove that the K theory mod p does not vanish, non-vanishing up to some of the p dimension of the residue field. Plus precisely this embedding dimension that I've erased here. So the dimension of m mod n squared that appears in the definition of regularities for the embedding dimension. And so let's maybe write it like this, up to the p embedding dimension. And then you see if your ring is a p dimension of a plus 1 regular, then you see that this map here is so and so connective, so you also have the same connectivity with mod p coefficients. And then so you see some of the maybe let's write it like this. So by this non-vanishing lemma, you have non-vanishing here up to so you have some of the p dimension of the residue field plus the embedding dimension. And on the other hand, on the K theory side, on the KH theory side, you have vanishing. So here's 0 and here non-zero. Starting from the dimension, and you see this can only be true if the embedding dimension is small enough. I mean, precisely equal to the dimension. And this gives you the regularity. So this is how you prove this. Let's indicate how you get these results. Actually, I realized I'm somewhat too fast. So let's start with this.
You can make a few more examples like this when vanishing.
Okay, let's start with this non-vanishing lemma maybe. So that's easy. So let's take A, let's say, as a local with maximum value M, and residue field K. And so we want to prove that this K3 does not vanish up to a certain degree, which has to do with the embedding dimension and the P dimension of this residue field. And so what can we do? So assume take elements, let's say y1 to ys units, first of all, in A's, so units in A which map to what is called P independent elements of K, so mapping to the residue field, independent elements of little k. So this essentially means that if you look at the images of these elements in your residue field, take their differentials, and then they are linearly independent. That's one way to say this. And also we take elements in the maximal ideal, let's say x1 to xr in the maximal ideal, which if I reduce them.
A and Fp-algebras in this lemma?
Sorry?
Is A and Fp-algebras in this lemma or only of residue characters?
That's an Fp-algebra, yeah, thanks. I mean, otherwise this notion of P independence and so on doesn't really make sense. I mean, P depends really on
The residue characters.
yes, you're right, but
Okay, but Fp-algebras.
yeah. But the thing okay, anyway. Yeah, let's stay with Fp-algebras. And you take elements in the maximal ideal such that also which I think somewhat linearly independent in the cotangent space in M mod N squared. Then you can form just a symbol, some product of K1 classes, and you check that it's non-zero, and it's precisely if you do the following. So you have these units which are K1 classes, so I can form their product, which is, I mean, usually classically these symbols are always denoted by these curly brackets. And these here, you can of course take 1 plus these elements, x1, and this is also a unit. And here you take 1 plus xr. These are all units, and so this is an element in K r plus s of your ring. And you can even take it with the Z mod P coefficients, let's say, and then this does not vanish. Okay, so you see that you get non-vanishing up to this S here, you can take S precisely up to the P dimension of the residue field, you can take R up to the embedding dimension, and you just have to check that this is non-zero, and this is in fact very simple, so this is, you just apply the trace map to Hochschild homology, ordinary Hochschild homology, so just Dennis trace map. So check. Hochschild homology relative to Fp. And this is also, you see where some of the P dimension of the residue field comes in, because by some of the Kühn formula for Hochschild homology, there's a term like the Hochschild homology of, okay, there's some reduction steps, but essentially this comes from the Hochschild homology of this residue field here over Fp. And by Hochschild plus and Rosenberg, that's precisely differential force. So this is where the P dimension comes from. At one point. Okay, so this is some of the easy part. And then there's this. So question so far.
So the unit goes to this log form thingy or what?
Yeah. Yeah, and you see this is precisely where you have this condition here that these are P independent precisely gives you that the image is non-zero and differential forms. So this was rather easy, and then there's this non-vanishing part, and this is really much deeper. So let's form like this. And we also say this is, so we proved this in our paper, and it's again somewhat in parallel, and also in fact by similar methods. It was also proven by Kelly and Morrow. And this says the following. Let's check. Yeah. So if X any Noetherian Excellent. Scheme. By the way, I wanted to say maybe this excellence condition is in particular satisfied if you have something of essentially of finite type over a field. Then the homotopy theory of X with multiple coefficients. So homotopy theory of X with multiple coefficients. This vanishes for I bigger than the p dimension. Okay, and this is really a deep theorem, or just, let's say that the proof. I mean, it combines a lot of recent results, deep results in K theory and topological cyclic homology in particular. And I want to sketch how you prove this. Yeah. So the first thing is that this homotopy K theory, this is somehow much nicer behaved than algebraic K theory. In particular, it satisfies something which is called CDH descent. Which is, so this is a topology on schemes where you allow, first of all, so it's finer than the Zariski topology, and you also allow certain coverings where a covering map could be proper, namely, for example, a blow-up map. You allow some blow-ups of a scheme in a sub-scheme. So this is a topology. This is somehow made for using resolutions of singularities. And this is also what has been used by Cortiñas and so on in positive characteristic, where we have resolution of singularities. So what?
Characteristic zero. Non-positive characters.
Yeah, what did I say?
Positive.
Okay, thanks. Good. And so this was proven by Zariski. And then someone. So now. I don't want to say it. Yeah. So yeah, okay. So it's somehow, so that's a topology, and it's known what the points are somehow. What the yeah. And then the points are precisely the spectra of Henselian valuation rings. And this means that to check certain things, you can always reduce to Henselian valuation rings. So in particular, this you reduce to the case of a valuation ring. So these are now, of course, no longer Noetherian, but you can still, I mean, the statement still makes sense. And then, yeah, so someone would say, so this X is now a spectrum of a valuation ring. And now we have learned in the example before for K n-regular rings that valuation rings are K n-regular for all n. So in particular, the K theory is again equivalent to the homotopy K theory. So this tells you that the K theory of B mod P is now this again KH. So we want to prove something about KH for general X, then somehow reduce to something more regular, and then we are back to K theory. So now we want to prove a vanishing theorem for.
Have you sort of used up the Noetherian hypothesis, or do you still know something about the valuation ring that comes from X being theory?
I mean, we know that you can even restrict to Henselians, and you can also restrict, I think, the dimension of the valuation rings. That yeah, that's also important that you can control the dimension. But what? No, we don't know anything more, I think.
So the Noetherian is somehow used in step one to reduce.
Yeah. And actually, I mean, I'm not completely sure, but it's probably by this work of E. Hick. So that's Elmonto, Hoyoa, Iwasa, and Kelly. It's maybe true if you can probably replace X Noetherian here by quasi-compact, quasi-separated, and of finite valuative dimension, because then the CDH side is still hypercomplete. This is what is important there.
What do we need excellent for then?
Yeah, I didn't write it in my notes, and then I just had the impression that I need it somewhere. And yeah, I'm not completely. Let's say this is definitely true. And but maybe you don't need it. Okay, so now we want to prove a vanishing statement for this. And this is where this work of Klaus and Matthew and Morrow is very helpful. So they prove. They prove the following surprising fact, namely that you have the cyclotomic trace map from K theory to topological cyclic homology, and so if you have any local Fp algebra, then the cyclotomic trace map is always injective, split injective even. So that's somehow very nice. So these are valuation links in particular. They are local, of course. So we have the split injectivity. I mean, injectivity is enough of K theory with P coefficients to Tc. So now we want to prove a vanishing statement for Tc. And okay, so there are more deep theorems to come somehow. So now we want to prove something about this, and there has been all this machinery by Butt and Scholze and so on, Butt, Morrow, Scholze, and these motivic filtrations. So there's a motivic filtration. I have a motivic filtration. On Tc of, let's say, okay, let's try it like this. Tc of R is the mod P coefficients for any, for let's say R's in Fp algebra. And you can describe the associated graded. So what are the graded pieces? So per n of Tc. What is this? This you can describe as the fiber of the following things. So you have something called derived differential forms. That's derived differential n forms of R. I mean, this just means you have your Fp algebra R, take a simplicial resolution by polynomial algebras. Then you apply the omega n form, the usual n forms, to this simplicial resolution, and then you take the realization. And this is the definition of these derived forms. And then there's another term, namely what you now do, you take the forms, but modulo the boundaries. So view this here as a functor and derive it in the same way, and then plug in R here. And then it's shifted by n. Okay, that's what it is. So in particular, you see that. So if you wouldn't have this L here, then this looks already quite good. So if this would be discrete, then this is only in degree n, and differential forms vanish above some kind of dimension, and so you can deduce a vanishing statement from this. But the problem is some of this that we derive here. So this could, of course, produce also homotopy groups in higher degrees. So this is something that you have to control. And so yeah, let me just maybe put here Hausdorff. I mean, for this filtration, because you can, I mean, Hausdorff somehow. So I mean, there's this old style definition of Tc, where you describe it as the fiber of. So let me see, I'm trying to explain where this comes from, where you describe it as the fiber between Tr, two copies of Tr with 1 minus, I didn't tell you what the map is, 1 minus Frobenius. And these Tr groups have been computed by Hausdorff in the case of let's say, polynomial Fp algebras. So then for polynomial Fp algebras, basically you get this formula here. And then, because we know that this here also commutes with colimits, by this paper by Klaus, Matthew, Morrow, you can somehow extend it to, just take the colimit over this simplicial resolution and you get this derived forms here. What is the map here? So this is similar to this 1 minus Frobenius that we have on the TRs, and in somehow if you mod out by P, then you get this here, and the map is 1 minus C inverse, where C inverse is the so-called inverse Cartier operator that you always have in characteristic P, so which sends a form x dy to some of the divided Frobenius. So this is precisely x to the p, then y to the p minus 1 and times dy. Okay, this is how this starts out. Okay.
There's one thing which makes me a little nervous. Do we have to complete somewhere? Like Hodge complete or something?
No. No, this Hodge completion only appears somehow in characteristic 0.
Yes, but TR doesn't somehow commute with the polar match, right?
Yes, but you have this, I mean this TR thing you only need for the polynomial things.
Yes.
And then I take,
Oh, and then you use the TC commit.
Yeah.
Right, but then okay, then it's not actually just this fiber on TR, but for polynomial, yeah.
Okay. So now you need, so what somehow remains is to control these derived, so now we want to plug in this formula which was standard, we want to plug in our valuation ring, V, and we want to control these terms that appear here. And this now uses another very deep theorem. So somehow if we had resolution of singularities, then we would know that every valuation ring I think is in smooth over Fp, and then you get this. These things are just discrete. And Gabor and Ramiro proved that this is in fact true. So without using a resolution of singularities. So just say, so what you do now is to plug in R is equal to V. And then we use the following theorem of Gabor and Ramiro that derived differential forms for valuation ring in characteristic P. This is just the usual differential forms in concentrated in degree 0. And they also prove that this here is a flat V module. And this here vanishes above some p-dimension thing, so this is somehow good. That's the first thing. So this allows you to control this term here, but then we also need to control this term here. And now it's of course we have somehow a new problem, because now we have first modded out by the boundaries, and we derive this functor, and but there the following Cartier isomorphism is helpful. So Gabor also proved that you have the Cartier isomorphism. Maybe I should say this, or this, Cartier iso. Namely, so the Cartier isomorphism, classical Cartier isomorphism says that this inverse Cartier operator, this induces an isomorphism between the forms, n forms, and the nth de Rham homology of your ring if the ring is smooth over Fp. And this is also something that is still true for valuation rings. So you prove that the de Rham homology of the valuation ring, this is isomorphic to the usual n forms. The de Rham homology is just homology of the de Rham progress via the Cartier operator. And this is some of the tool that you use to control these de Rham homologies, or derived de Rham homology in positive characteristics. I think this was first observed or used by Bargaf Butt in his papers. So for in the smooth case, and Gabor proved this also for valuation rings, so we can now somehow use this, and then you see, so we have good control about these, the derived functions of this thing, so we also have good control about the derived somehow de Rham cohomologies, so derivation of these cohomology functors, and then you do some induction over n, so use this sequence like, what is it? I mean, cycles map to, boundaries map to cycles map to cohomology, and boundaries map to the whole thing and map to this quotient here, and then you do some induction and then you get the result. So now induction. Just the desired. Sorry. induction gives that in fact all these things are discrete, so also that this derived quotient here is just concentrated in degree 0. And then finally we need one more fact, and namely this vanishing. That's also something that Gabriel Romero proved. So what did they prove? That the differential force that they appear here now in this formula, they embed injectively in the several forms of the fraction field. This is essentially this flatness condition that I mentioned before, and that they also proved that this is a flat V module. This implies that this is injective, and this is of course 0 for n bigger than the p dimension of the fraction field, which is less than equal to the p dimension of the variation ring. So you see, if n is bigger than the p dimension of b, then it vanishes. Okay, so that's basically maybe one very last thing is just wanted to note that this vanishing here, this is really sharp. I mean, not for a particular x, but you can just plug in a field, and then we know precisely that the KH theory does not vanish with mod p coefficients up to the p dimension of this field. So you see, with this method, we cannot prove a better somehow version of this conjecture than the one that I stated. Okay, so let me stop here.